Anyone studying Western music theory will be introduced to the concept of harmonic functionality, the idea that chords in a piece of tonal music may be categorized into three groups: tonic, subdominant, and dominant. This was one of the many theoretical innovations, many of which we use today, by the German music theorist and musicologist Hugo Riemann. Riemann was interested in a wide variety of theories, and among these was the idea of harmonic dualism. Dualism takes the idea that the major triad emerges naturally from the harmonic series and inverts the series to explain the minor triad. Harry Partch did the same thing to get his otonality and eutonality concepts. Riemann would later disavow the notion of dualism as an explanation for the minor scale, but the idea that minor is an inversion of major stuck around. 20th century pitch class set theory did the same thing by looking at the intervals of both chords. And if you're familiar with the idea of negative harmony, it has a lot of overlap. If you build a major third and then a minor third up from C, you get C major. But you build the same interval pattern down from C, and you get F minor. In this theory, the root of the chord isn't necessarily what you'd expect, or even track. C major can be represented by C plus, because you're building up from C, but F minor, building down with those same intervals from C, can be represented as C minus. Neo-Riemannian theory is a branch of musical analysis that's devoted to understanding a gap between traditional tonal harmony on one side and complete atonality on the other. Composers of the late Romantic era like to play around with triads, the surface-level component of tonal organization, without adhering to the underlying substrate. That is, where do triads come from? I mean, the harmonic series, sure, but ultimately their function in tonal music is to express what key you're in and where in that key you were. So to use triads without key was novel. Just like you took all the sounds present in a language and then you randomized them. And there's only so far you can take this concept before composers began wondering, well, if we're no longer concerned with key, why are we limiting ourselves to the sounds of that language if the precepts by which those sounds were derived, that is key and tonality, was no longer playing an active role? This is where atonality and then the 12-tone system and other forms of musical structure began to emerge. But there was this middle period where triads were still around, but tonality wasn't. This left some of the most orally compelling music of the late 19th and early 20th centuries. That is, composers who use tonal harmonies without using functional tonality, without substantive literature on how we can analyze and understand it. This is Strauss, this is Debussy, this is Rimsky-Korsakov, this is Wagner, right? No small names. Based on the work of Hugo Riemann, a group of theorists including David Lewin, Richard Cohn, Henry Klumpenhauer, and Brian Heyer came up with a set of operations that may be performed on triads of different qualities without regard for overarching tonal organization. It takes minor and major triads as a priori constructions that mirror one another in interesting ways. So it is perfect for taking a look at music that uses triads without reference to key. This is an example of a kind of music theory that is trying to analyze triadic atonality. People think that atonality just means music that is intentionally dissonant, but this is a case from a technical perspective. Any music that does not comply with common practice tonality is atonal. Because Neo-Riemannian analysis makes neither presumptions nor predictions about the piece from which a given excerpt is pulled, it is unmoored from having to explain everything in its purview in the context of an entire piece. Instead, triads are related only to themselves in their surrounding immediate context through a series of operations that take major chords and transform them into minor chords, or vice versa. Riemann's writings on harmonic dualism find footing in these operations, which are entirely invertible. Invertibility in these operations is the key component. If you begin with a triad of one quality and perform one of these operations to get a triad of a different quality, performing that same operation on the second chord that you get will just give you your original chord again. So only minor and major are able to work in this system. You're not going to find diminished or augmented chords anywhere. These basic operations to convert major into minor and vice versa are P, R, and L. So if you've gotten to this point in the video, you probably already know the concept of parallel and relative chords and keys. We already think of these concepts dualistically, right? If you have a major key, you can have a parallel minor and you can have a relative minor. While in a minor key, you can have a parallel major and a relative major. It's not possible for a minor key to have its own relative minor, or a major key to have its own parallel major. So P and R, they stand for parallel and relative. They're familiar operations, just keeping two common tones from a starting major chord and replacing one note with one a step away. L stands for Leittonwechsel, which is a German term translating to leading tone exchange. This operation replaces the root of a major chord with a note a half step below it, the leading tone. Like the other two, this is a dualistic operation because this is not a more familiar theory term. You might think that if you started in C major and performed L to get E minor, you could just perform L again and get G augmented, and then B major, and so on. But this doesn't work because the exchange needs to be as dualistic as P and R. No augmented chords allowed. L and P are functions that exhibit a property known as maximally smooth voice leading. The idea here is that the best possible voice leading has A, as many common tones as possible, and B, that voices that move should move by as little as possible. In order for it to be maximally smooth, you need to move it by half step. So R, with its whole tone motion, is smooth, but it's not as smooth a voice leading as the other two. Because two notes stay the same as these operations unfold, the interval that they create will be maintained. P will always retain the perfect fifth, R will always retain the major third, and L will always retain the minor third. These functions retain two common tones, but what if we expand these functions to include voice leading where there is only one or no common tones? These are known as secondary transformations because they take the basic transformations and apply them in certain orders. You can think of the basic operations as sort of the lowest common denominators. And so there are many possible secondary functions, but the ones that are most commonly used in the literature are N, which stands for Nebenverwandt, a German word that roughly translates to secondarily related, which preserves the root of a major chord and takes the other two notes just up a half step. There's also S for slide, where the mediant of a chord is preserved and the outer fifth moves in parallel motion. And there's also my personal favorite, H, which stands for the hexatonic pole. No common tones are preserved in this one. H relates to the hexatonic scale, which alternates half steps and minor thirds. You can think of this as kind of related to the whole tone scale, but just where one of the augmented triads has been displaced by a half step. So starting on C, the notes that you need to get a hexatonic scale would be B, E flat, and A flat, which can then be enharmonically spelled as A flat minor. The opening of Ray Vaughan Williams' C Symphony starts with an H relationship. So when you take a triad and its H-related triad, you will get a hexatonic collection. And because there are only 12 notes, there are only 4 discrete hexatonic collections. What's missing in Neo-Riemannian analysis is the tonal dominant tonic relationship, which makes sense because this wasn't designed to analyze music that used tonal cadences. The dualistic nature of these Neo-Riemannian operations, with these letters standing for these little machines that swap back and forth between two chords of different qualities in specific ways, means that it's possible to construct a shorthand for any relationship between two chords that you want to define even arbitrarily. Christopher Segall, to analyze Alfred Schnittke's use of triads, defines M as the relationship between a major triad and a minor chord, a minor third up. Neo-Riemannian analysis can look incredibly beautiful, as chords can be connected in a lattice called the tonets, where everything is connected to everything else. So while you can define M as P, R, and P, arranged in that order, unless you're getting from point A to point B using those operations, most of the time, composers aren't doing that. There has to just be a better way of talking about these things rather than using an unstandardized system of secondary relationships using capital letters. So Neo-Riemannians have come up with an efficient shorthand called uniform triadic transformations, or UTTs, as offered up by Julian in 2002. A UTT consists of 3 elements. There's a plus or minus sign, and then 2 numbers which usually add up to 12. The plus or minus tells us if we keep the mode or swap it for the other. The first number tells us how many semitones to transpose it up if the input is major, and the second how many semitones to move it up if the input is minor. A UTT is sort of like an algebra function. You input something, in this case a triad, and the UTT will tell you exactly what you're supposed to do with it. All Neo-Riemannian transformations can be mapped as UTTs. The reason these 2 numbers have to add up to 12 is to make them reversible. The M function can be represented as -3, 9. It flips the incoming triad and then moves it up 3 half steps if it's major, but a minor chord will switch to major and go up 9 half steps. We're working in a sort of base 12 system here, because you only got 12 notes. If these numbers do not add up to 12, or if there's a positive sign, they can create chains of chords. This is how you can reverse engineer the circle of fifths, for instance. Each and every one of the Riemannian UTTs are charted in Hooke's 2002 article, where he defines all dualistic UTTs along with their Riemannian names, how you get to them using the basic transformations, and other columns that categorize pretty much every previous attempt at organizing these relationships. What pops out here are the Schritts and the Wechsels, which stand for step and exchange. Schritts have positive UTTs, which means that they create chains of chords. So using the Gegenleitung Schritt, which translates to step against the leading tone, the quality of the chord is preserved and C major moves up to D flat major. But applying the Gegenleitung Schritt a second time leads to D major, then E flat major, and so on. This allows us to measure the furthest possible point away from the input chord. Tonally, we think of the tritone as the biggest tonal shift. And you might think that the H relationship we looked at earlier was pretty wild. But according to this table, the Gegenquintwechsel, which transforms C major into B flat minor and back, is the furthest any 2 chords can be. It's the only relationship where you need 5 basic relation steps to get from point A to point B. This makes it the tonette's pole. It is the furthest possible point on this lattice structure away from whatever you defined your starting point as. Going any further into Neo-Riemannian theory would involve a deep dive into a lot of very complicated looking mathematical equations, their proofs, and intimidating diagrams. But this is just an introduction, so we're going to have to stop here and ask ourselves a final question. Why isn't this more commonly taught? When most people learn about Neo-Riemannian theory, their response is that the system is incredibly elegant and beautiful, but that it's not a branch of theory that gets taught a lot, certainly not before grad school, and they wonder why. And the answer to that is more than the fact that academia, and academic music theory in particular, is resistant to changing what they've been doing for hundreds of years. I mean, the Neo-Riemannian theorists aren't all dead. The issue has to do with the limits of Neo-Riemannian theory more than anything else. When you compare Neo-Riemannian operations to Heinrich Schenker's theories, you'll find that they're really narrow in scope when it comes to what they can explain. But Schenker's theories are concerned with the totality of a piece of music. Schenker proposed a sort of music theory equivalent of a theory of everything. Whether you think his theories are valid is irrelevant. It's the scope, it's the audacity of a theory that's the selling point. The same goes for Roman numeral analysis, pitch class, set theory, etc. They can explain what happens not just moment to moment in a piece, but over the course of an entire long work. And that's just not what Neo-Riemannian analysis is about. These theorists focus narrowly on certain inexplicable passages in certain pieces to explain how they work. Neo-Riemannian theory proposes no overarching system of what's happening globally. This thinking is still in its infancy, and it just hasn't had enough time to take root and develop. In time, it may become a core part of the theory curriculum. I certainly hope so. I wouldn't be making a video on it if I didn't think it was interesting. Part of it may be a need for more music that uses Neo-Riemannian concepts over the course of a whole piece, and not just in unusual moments or voice-leading idiosyncrasies. The theory is stuck analyzing leftover scraps of music that can't be better explained in other ways using other theories. Reading the analytical literature makes me think I'm in dereliction of my duty as a composer. Like, we gotta go out there and we gotta write some Neo-Riemannian music, and we gotta keep our music theory people employed. Yeah!